And I kind of want to draw a parallel here between the 1940s, where the first electronic computers are invented. At that time, I call it an age of extreme scale serialism. Why? Because previously, computation is done by computers, human computers. It's actually massively parallel. You have a full room of people doing calculations. And that time, people figure out, okay, you can use vacuum tubes to do computation. It's much, much, much faster. But what does that require is that it requires a very simple, scalable digital operation that can be implemented with a few vacuum tubes. So what is adopted at that time is this, the binary digit. It turns out with binaries, you can implement a lot of calculations with very simple electronics, vacuum tubes. You can do this with decimal digits, but it may require 10 times as many vacuum tubes, and it's not going to be as reliable as with binaries. I want to draw a parallel with today. That is, we are in an age of extreme scale parallelism. With extreme scale parallelism, I think the focus is not on computation, but on communication. Because these many computers, they have very complex memory hierarchy. They have to communicate with each other in very different ways, depending on what memory hierarchy you are in, GPUs, CPUs, nodes, whatever. That requires a very simple and scalable communication pattern, right? Just like the binary digit we have in the 1940s. And I think that the key is you want to, for solving PDEs, I think that means you need a compact stage. You need a communication pattern that only accesses immediate neighbors. So for example, this is kind of my pet project for the last few months. So for example, you can do the project. I want you to be able to describe a numerical scheme for solving PDEs in the same way as you would describe to another human being on the whiteboard. For example, if you have I-1, you would just say u.in. If you have I+1, you just say u.I+. And I want to be able to decompose a formula like this into compact stages. First, you represent this update formula with a graph. And the computation graph is similar to what you have in, let's say, in automatic differentiation. But you have these special edges, the blue and red edges, that accesses the neighboring grid points. This particular formula accesses two layers of grid points. So if you trace from the input to the output, some of the paths has to go through two levels, or two of these special edges. And then you need to decompose this formula in such a way that, okay, so these are, each node is an intermediate variable. And you want to decompose the formula in such a way that each compact stage does not contain any path with more than one of these special edges. Okay, so if a stage has a path that contains two of these special edges, then you are accessing neighbor of neighbors. So this becomes a very interesting mathematical problem.
So I'm sorry, I didn't get that. So what are the special edges?
The special edges are access to neighbors. For example, if you look at between 0 and 3, so 0 is U0, 3 is U0.xp, so it's U0 at the positive neighbor grid point. So you're accessing your neighbor grid point. These special edges are neighbor access. If a path goes through two special edges, then the output, the final point of that path, has to access two level of neighbors of the starting point of that path. So it's a graph theoretical problem. So what we do is we use operator overloading to convert the Python code into a graph. And it turns out the decomposition problem can be formulated with the integer programming problem. And this is called Shannon here. I put in here because the way I followed in posing that integer programming problem is almost exactly the way people figure out the max flow min cut. Max flow min cut problem, which is I attribute to Shannon. But what's special about this is that you can also prove that the integer programming problem has a totally unimodular constraint matrix that is the constraint matrix. If you take any square submatrix, it has determinant only -1, 0, or 1. So instead of solving an integer programming problem, which is very complex, you can solve a linear programming problem. So that's great. And then the integer, after you decompose the graph, you rebuild the subgraphs, and you can translate the subgraph into C and MPI code, compile that into a shared library. You can broadcast, you can load the library into memory, broadcast it into as many MPI ranks as you want, and the MPI ranks load that into memory, and you run it, you get the result, basically with the push of a button from that code. And for example, this is the same graph, but for an actual Euler equation solver in 2D second order skew symmetric discretization. It's not finite volume, but conservative finite difference with fourth order Runge cutoff. So the decomposition is into 8 stages. Sorry, I think the screen cut the input and output, but like you have 8 stages, and the linear program actually is several thousand by several thousand. It can be solved in less than a second. So it's fantastic, and so the linear program actually minimizes how much communication you actually have. So an average of 17 numbers are passed per stage. That's how many numbers you are communicating in between your neighboring process.